Great to see you here again. In the previous video, we looked at the definition of sets, and in this new video, we will continue with our knowledge and we are going to describe what a Venn diagram is, what are subsets, how can we define the set or the size of a set, and what are power sets. The first thing what we can do is to look at Venn diagrams. And a Venn diagram was invented by an English mathematician, John Venn, in 1881. And it's in fact based on the set theory, it's basis of the set theory, where we first consider a universal set U, which contains all the elements which are under consideration. And we represent this in a rectangle with indication U, the universal set. It can be all the students of a school, it can be all the real numbers. Whatever it is, it contains all the elements that we are considering. Another element is when we look in the universal set, we can draw circles or ellipses that represent partial elements of the set, of the universal set. So we can make what we call a subpart of the universal set. And we look at the universal set when we, for example, consider all the natural numbers. And the natural numbers, like I said, we can still discuss is zero included or not. It's basically not important this moment, because I look at the odd natural numbers. And the odd natural numbers are 1, 3, 5, 7, and 9. So within that universal set of the natural numbers, I defined a set which contains all the natural numbers which are odd and which are below 10. Now we can continue here and we can look at the definition of a subset. So we had a subset, we had a set, but we can also consider a specific set that is a part of an other set. And we call this a subset. And we can say that the set A is a subset of B, if and only if every element of A is also an element of B. And we use the notation A with a C with an underscore B. So basically, this also means that they can be equal. In the worst possible cases, we can have that those two sets are equal when all their elements are equal, and then the subset is in fact equal to the other set. Now let's have a look at the set we've seen before, and we consider now the other set, another set B, which contains all the natural numbers up to 10. And I didn't include 0, so now we see that the set B basically has the numbers from 1 to 10. The set A only has the odd integers, so now we can say that the elements of the set A are a part of the set B, and we call A the subset of B. Now we can also go further, because A and B are also subsets of the natural numbers of the universal set. So once we have the universal set, and every set we define within the universal set will also be a subset of the universal set. In order to continue, we have to look at some properties and definitions related to these sets. And we can describe a first theorem saying that every non-empty set A has at least two subsets, which are the empty set and the set A itself. And it can be expressed as the empty set is a subset of A, and A is a subset of itself. In this case, we have the equality sign that we have, the same value like the equality sign like we have in mathematics. We can also define the term what is a proper subset. We can write it as A is a subset of B, a proper subset. We lose the equality sign in the subset indicator, and we say that there is at least one element B of the set B that is not an element of A. So at least one element of B does not belong of A. And then we can say that A is a proper subset of B. Like the example we had before, where we had the natural numbers, we had the odd natural numbers, and we had the natural numbers up to 10. And in that case, the odd natural numbers are in fact a proper subset of the natural numbers up to 10. Now, another thing we can also deduct from this, when A is a subset of B and B is a subset of A, they're not proper subsets, they are normal subsets, then we can say that the two sets are equal to each other. Another element which is important in discrete mathematics is the size of a set. In discrete mathematics, sets are used in counting problems, and it's therefore very important to know how many elements are in a set, and we call that the size of a set or its cardinality. We consider a set A. It contains exactly n distinct elements, n being a non-negative integer. Then we call the set A a finite set with cardinality n, and it is written as the cardinality of the set or the cardinality of n. Now we can use it or we can use the cardinality. Cardinality comes from the cardinal numbers, and we want to count how many numbers that are in a set. Another element we can have when we have an infinite set, at that moment the cardinality is infinite, and we can define an infinite set as a set that is not finite. When we have a finite number of elements, it means that we can count them. We can say n is a specific value. If we cannot define n, if it continues going on, then the set becomes infinite and it's not finite anymore. Another term which is very important in sets and discrete mathematics is what we call power sets. And we can define a power set as the following set. We consider a set A, and we can define the power set of A, which is indicated as the P of A, which is the set of all the subsets of A. So we have to look at all the possible subsets. And let's have a look at an example to show you what this means. We have a set A, and the set A is composed of three elements, A, B, and C. And now we have to find what is the power set A, or the power set of A. Now, what are the subsets? First of all, we have the empty set. We have the set containing only A. We have the set containing B. We have the set containing C. So these three sets are singletons. And then we have the set A and B, A and C, B and C, and basically the last one is ABC. And we can write the power set of A as the set which contains all these subsets. So in this case, the first subset is the empty set. Then we have the three singletons A, B, and C. Then we have the sets AB, AC, and BC. And the final set is A itself. It's ABC. So these were very important definitions related to sets, and we will be using them later in the course in discrete mathematics. The next video, the next session, will be about the Cartesian products of sets, and we will continue our second paragraph here in this chapter. Now, you're doing a great job, a lot of work to do, but I'm sure that you get through it. So I thank you for your attention, and I'm looking forward to seeing you in the next presentation. Thank you, and bye-bye.